So guys, welcome again to the continuation of elasticity. And about elasticity, we have talked about a lot of things, and we want to do in continuation to what we have discussed. And now we have, this is where we stopped, and in continuation, we have types of modulus of elasticity. It is going to be a short class, short in the sense that it is the concluding part of elasticity and what is required. Like I said, there are different types of modulus of elasticity. We said in the last class that the modulus of elasticity is the constant that is coming from stress and strain, if you still remember. And about that, we can write. I think we need to put down this note that, fine, I think we are back. Yeah. So now we have, we can say modulus of elasticity. We can say modulus, we can write that to understand very well. Modulus of elasticity is the measure, I think it's better to write because of definition, is the measure of how elastic a material is. So it's the measure of how elastic a material is, and it is also defined, I think it's better like this, but some of us are writing SSCE, that is junior exam. Now it is also defined as the measure of stiffness. Measure of stiffness, stiffness. The measure of stiffness of a material. So please keep this at the back of your mind, because some of the time you might be asked to explain the definition. And in continuation to that, we said there are different types of modulus of elasticity. In junior classes, most of us are introduced to Young modulus, which it is one of the types. So about types, you can also write in continuation. Sorry about the pace. We said there are different types. We have three types of modulus of elasticity. The first one is Young modulus, which is popular from early classes. The second one is what we call bulk modulus. Bulk modulus. Please don't make me think about all this. It is all these things are very important for you to know. And the last one is a shear modulus. If you are following the class, you are going to see that when we talk about more of the stress and the strain, we said there is shear stress, there is shear strain. Now there's also shear modulus. So I think shear is repeating itself in all what we have been talking about. So keep that at the back of your mind. It's very, very important to know. And when we talk about Young modulus, like I said, more of this will be done by explanation. And from what you can see at the back of me, you can see the illustration. We talk about Young modulus. We are talking about the type of modulus, which is also what we have to keep in mind. It's only going to occur in solid. So, and when you talk about solids, you know what I mean by solid, not fluids. They are not liquid and gas. So Young modulus only occur in solid, and it is denoted by Y. I think maybe we should put down a note, but writing is not that easy, but we just have to put down a note, excuse me. From what we have learned before, we said that we can say Young modulus is as a result of change in length. Change in length. So generally, mathematically, it is given as, it is denoted by Y. Keep that at the back of your mind. Young modulus is denoted by Y, and it is given as, that is the stress, that is longitudinal stress. Let me help you put it well. Longitudinal stress over longitudinal strain. Longitudinal stress divided by longitudinal stress. Students should not make mistake when you talk about longitudinal stress and strain. You are talking about change in length. So be careful about that. So it's as a result of change in what? In length, and it's denoted by what? You know, the word modulus of elasticity in the previous class was denoted by E. When we relate the stress, we said it's proportional to the strain, according to Hooke's law. Remember? Very good. So now, when we try to relate stress is now equals to, we now bring the word constant of united we call E. And that E is called modulus of elasticity. So from there, the modulus of elasticity is now equals to the stress divided by the strain, which was discussed in the last class. So students should be careful about this. We now say this modulus of elasticity are of three types. Young modulus, which measures the variation in length. Bulk modulus, which is the next one we want to talk about, which definitely will measure the change in what? Volume. And shear modulus, which is variation in what? Tangential, we've talked about tangential line and what? A normal line. So now, for now, students should be careful about how to get formula to this and not make mistake in each of them. So we can continue with the formula of this one, since we have already discussed that stress is what? The force by what? Area. And longitudinal strain, we discussed that in the last class, is change in the what? In the length divided by the actual length. So what I'm trying to say, mathematically, the Young modulus we denote by Y can be written anyhow you want to write it. You can say F by L over A by delta L. Anyhow you want to write it, when you cross multiply, you are going to have your answer. And if you are not so good in how I come about F by L, this is what I have done. There is a division sign. This is delta L divided by L. I'm trying to show all processes for you to see. It is even at the back of me. So you can do this directly. This will come up, and that is why I said FL, and this will come down when you change this to multiplication over A delta L. This is area, and this is what? Change in length. So this is the formula we use in physics to calculate the Young modulus of the material, which is also very important for you to keep at the back of your mind in case of illustrations and numericals. The next is bulk modulus, and about bulk modulus, we can write bulk modulus. For students to see this clearly, because I can see most of them, you say you don't see the red ink, let me quick to change to green. And about this, we can say it is due to what we can write. We can say it is only applicable, just right, it is only applicable to fluids. And I believe we've been talking about fluids all these days. It means the what? The liquids and the gases. So now, my dear student, when we say it's applicable to fluids, so we say it is denoted. You can also write another point. It is denoted by the symbol B. Please note that. Bulk modulus is denoted by the symbol B, and it is as a result, another point, it is as a result of change in volume. No, you can write it is as a result of change in volume of the material. So keep that at the back of your mind. Remember the volume strain, we talk about change in volume over actual volume. But when it comes to modulus, it is called bulk modulus. So it occurs in fluids. When we talk about fluids, we are talking about change in pressure as a result of what's that. When pressure is decreasing, the impact of pressure on volume. And this you've studied mostly in your chemistry concepts. Now, not to waste time, we can also put it at the back of our mind that bulk modulus is expressed mathematically in continuation. I said it is what we call volume stress, because of questions, over volume strain. Volume stress over volume strain. Longitudinal stress over longitudinal strain is Young modulus. Bulk modulus is volume stress over volume strain. And when we talk about volume, everybody should note this. When we talk about volume stress, we are talking about change in pressure. Please note that. So volume stress generally is given as change in pressure. And volume strain, we've discussed about that. We've talked about change in volume, that is delta V over the actual volume. So please be careful about most of this time, the change in pressure, because pressure is going down in physics. We denote it by negative. So, but in calculations and numerical, we don't always put this word a negative sign. So most especially when I say negative here, I can put it in modulo. In most of your material, you might see modulo form, and you know what that means. Absolute form, absolute value. So basically, it is always negative, because if you are doing some exam that is more technical, they might actually want to test if you understand, and you might have those ones that has negative, and you might be thinking, which one are you going to pick? So be careful about that. But when it is in modulo, you know, the modulo of negative number is positive. We now say a change in pressure is a volume stress over, you can say, change in volume over volume is the strain. So which you can also make sort of formula, but you can as well directly keep this at the back of your mind, so that you will use that directly to solve questions that involves modulus. And the last type of modulus of elasticity, which we call our shear modulus, is very simple. It's also only applicable for what? For solids. Please note that. But the shear modulus, which is the type of modulus of elasticity, modulus or modulis, if there are more than one. So the shear modulus, I said, is only applicable for solids, just like your Young modulus for solids. And directly it is given as we say it is given directly as a shear stress over shear strain. So you can just write shear modulus is given numerically as the ratio of shear stress divided by the shear strain. So keep this at the back of your mind directly, as we've talked about shear stress before, and we've talked about shear strain as well. Shear stress, you know, it's force over area, the force that is acting tangentially. And the shear strain, we talked about that is that small angle theta in our last class, which is something as H by S. So this is the way we represent this, and please be careful about this in your examination and not to make mistake on how to use the formula. You can keep the formulas in mind, but the formula is the most important thing. And another thing I think I need to talk about before we move to the next slide is for you to know that there is another relationship we call compressibility. Please let it be known. Compressibility, you can write that before we move. Compressibility of a material. You know the meaning of compressibility, to compress substances. Now, compressibility or compressibility is always equals to inverse of the bulk modulus. I hope students understand this. So next time you have questions that is asking you about the compressibility of a material, just keep it at the back of your mind that it is what? The inverse relationship of bulk modulus. So if they ask you what is the compressibility of a material, what you need to calculate is calculate the bulk modulus of that substances in numericals, then go for the inverse or reciprocal, the way you might call it. So guys, be careful about this. Don't make silly mistakes when it comes to numerical. And as you all know, this is concept video class. Numerical chapters are always available for each of these, which are other videos. What we do here is just illustrations, which are not enough for you to actually know how to solve our numerical. So concept class is only for us to give one or two illustrations as being prepared by the student. Now we move to the next one. So in continuation to that, we move to the next slide. Fine. Now, about the next slide, what we have here is to talk about some facts of elasticity. Yes, we need to understand some facts so that we don't make mistake when we are faced with some questions about non-numericals. Now, about facts about viscosity, let us quickly just write that as we have discussed in the last slide, I think it's important to recall that the modulus of elasticity, you can just write modulus of elasticity is the measure of stiffness. I think I talked about that in the last class, but I didn't give more illustration about that. Now, to understand this very well, as we have discussed, we said modulus of elasticity we denote by E is equals to the stress divided by the strain. Very good. Now, from here, we can conclude as a physicist that as what? The stress is being increased, the modulus of elasticity tends to increase. And as strain is being increased, the modulus of elasticity will be decreased from this relationship. That is talking about inverse and what? And direct. Now, my point here is not that long. What I just want you guys to know here is that we need to understand that when you increase the modulus of elasticity, which is what I want to try and show here, as you increase the modulus of elasticity, you can see what happened to the strain. The strain will be decreased. And we define strain when something is deformed as a result of force, the apparent change or the change in size or shape or the structure of that material is called its strain. From what you can see at my back, if you can actually see what is showing at my back, you can see that we have a material of length. When it was stretched to a point of the air, we've talked about this before, time and time again. Now, the apparent change in the new length divided by the old length, we call the strain, which we have studied, which we have already studied. But what I'm trying to bring out here is a little bit of understanding of a little more concept. Now, let us quickly look into this. Look at this. Maybe we have two wire, maybe we have two wire or string. Let's take an example like we have a wire that is elongated or that is being stressed by a force up to this length. And we have another wire, which is, sorry about that, I want to make it more glaring. We have another wire which is very, very rigid, like this. And by the same application of force, it was only being stretched to this particular point. Now, talking about this now, we can talk about which one is more elastic. Now, from your knowledge in early classes, I know everybody will go with what the first one, that this is more elastic than this. Why? Because it is more stretched. So that concept is what I want to tackle here on my first fact of elasticity. Students should be careful that a wire that has this is the same amount of force was applied on these two strings. One is more stretched than the other. The one that is more stretched than the other has more strain. From what you can see on my back, I don't know if you can see that. You can see the length now. Now, the first length of that particular wire was that position, or the metal rod, or whatever you call it. When it was to look at the blue section, blue. Now, looking at that one, it was now it is now more stretched, a bit, because of the strain. Now, what we are trying to say now is that the strain has increased in a wire that is more stressed than that of the one that is less stressed. So from our relationship mathematically, which I believe will be more understandable for most of us, we can say the wire at the first one, let's say this is figure 1 and this is figure 2. According to this directly, we can say there is more strain in this one than this. And if there is more strain in the first wire, that means it's going to have less modulus of elasticity. And we also said the modulus of elasticity is a measure of how elastic, the elastic property of a material. I think I talked about that in the last slide, that the measure of elastic property of a material is by the modulus of elasticity. So my point now here is that you should understand now that this one that has less strain, we have high modulus of elasticity, and hence wire 2 here, or whatever, rod 2 or string 2 is going to have more it's more elastic than the first one. So the point of actually telling you this part is for most students that you may have a misconception in understanding this part. That is, what we are trying to say is that the wire that has a less strain is going to have it's more elastic. So you can also keep a note down, I think, which is important for us to also keep him at the back of our mind with respect to what I've explained. For more understanding, we can say that okay, I think it's better like this. The elastic property, please write the elastic property, still in continuation to what I've explained, the elastic property of a material is measured. It's measured by its modulus of elasticity. I hope students understand that, which is just what I have been saying since morning. So note that if you if the Young modulus is high, that means it is more elastic. That is what we are saying. So there's a lot of misconception on this. For example, I ask you that between a rubber, let me just ask a simple question, between a rubber and a metal, which is more what? Which is more elastic? 95% of the students from my survey in my classroom picked rubber. So, and this is why we need to talk about this. I've gladly explained this before, but I'm trying to make everything with respect to the way we are doing in the syllabus. So now, be careful that what metal is more elastic, according to what I've explained now. Metal is more elastic than rubber. So always keep that at the back of your mind, than rubber. The reason is because what? The strain in rubber is higher than what? That in metal. So more elastic than rubber. So this is what I want to clear here. And that is why I actually created this fact. And we can also write in conclusion that in terms of elasticity, I say elasticity increases, just in continuation to also what I've talked about, elasticity increases in a sequence of, you can say, solids is more elastic than liquids, and liquids is more elastic than gases. I think that will also help you to understand what I have talked about. So keep that at the back of your mind. And I think I can add one more to this, talking about the effect of temperature. What about that? It's simple. When I introduced you to the topic of elasticity, I made you understand that when you talk about elasticity, you have to keep it in mind as a result of intermolecular force. And I've been always saying this, that most of the things we explain under this chapter is always about intermolecular forces and the neighboring, the one and the constituent element. As they interact with each other, you are going to have a result of their interaction. So the study of this result are mostly what we do in fluids, in wires, and all these things that we have been talking about. In fact, mostly in physics, in mechanics. So keep that at the back of your mind. And if we are talking about effect of temperature, because I have seen questions from a lot of past questions over the years that ask about the effect of temperature on elasticity, it is very easy to know. It is not always all what instructor teachers like us are going to teach you. There are some things from what you have learned in concept you can conclude from your own understanding. Now, what is the effect of temperature on the intermolecular forces? It goes without saying. When temperature is increased, the intermolecular forces will reduce. So when intermolecular forces reduce, what happens to the elasticity? They also what? Do you understand now? The modulus of elasticity will reduce. So when modulus of elasticity reduces, what happens to elasticity? They also what? Reduces. So you can just write in notes, or you to have a note that increase in temperature, which is the last thing I'll talk about, increase in temperature lowers the elasticity of the substance. I hope you understand that as I've explained, because elasticity is due to intermolecular force between neighboring atoms or neighboring particles. So this is what I want to talk about when I talk about some fact about viscosity, which students need to keep in mind. And we move to the next slide. Yes, the conclusion of this part of our syllabus is the last part of it, which is given according to the syllabus. Like I said, we are working with respect to the syllabuses. Elastic potential energy stored due to elasticity and the energy density. Here we are going to be deriving the formula as usual. And also don't forget, it is not only by deriving the formula, we are also going to use the formula to solve questions. Some of us, we already know the formula by heart. Yes, fine, good. And some of us who are not so good in deriving formula, should keep it at the back of your mind that these formulas are always important. If you are not good in deriving, you should try and know. That is why I always tell you to keep it in mind. So it's always good to keep it in mind, because if you don't keep them in mind, when needed, you might fall a victim of not getting them. So directly, let's start about elastic potential energy. About elastic potential energy, we can say, we have talked about this before. If you can recall, we said when a material is being stretched. Let's write. I think we need to write I'm running away from writing. So I said when a material or when a substance, anyhow, when a material is stretched, material is stretched, work is done. Work is done on the body. These are simple things. I know you understand from what you've been talking about before and before. So because the distance is being covered. Now, when you try to stretch your material, you are changing the distance by distance of delta x. So the force in the line of the distance is called what? The work done. So, and because work is done, you also know from my way of explaining, this is not the first time of hearing me saying this, because work is done in moving that material from one position to other. You can also say that what the body, please write, the body will store some elastic potential energy. Some elastic potential energy. So students should keep this at the back of their mind, that when work is done on the body, you know that what the particular body or material or wire or strings or anything you want to call it, just like your string tool, is going to store what we call what some potential energy in it. And you know from early classes that potential energy is what? The energy that is being stored, which everybody knows. Some people will say energy due to the position. Yes, you are right. So now, to understand this very well, that means what we are trying to say is that well, a wire can also behave like a string, because when it is being stretched, what happens? It's going to store a potential energy. So be that as it may, as we have already studied that the Young modulus, so because we are talking about length, I want to talk about length. What are we talking about? We are talking about Young modulus. Fine. Now, we can also say, here I believe you guys can hear me, and you can hear me well, and you are flowing with it, because I'm not going to be the only one in this. We are going to derive it together. So I need you guys to communicate this time around. Now, from Young modulus, we've talked about Young modulus. We said Young modulus is denoted by Y, but for now, for you to follow through, I'm going to put it in time of full. We said it's given by, remember, they said stress over strain, which is a F by L. In the previous slide, we've talked about this, divided by delta L extension by L. Hope you've not forgotten this, or you say data extension produced over original length. Let me say the extension is E. I will take the extension as E now for understanding, so that L will not cause issue, because L is too much there. So we have the extension. I will take the extension as E. It's the same thing. Extension is delta L, because L. This is force over area. Please let it be known. I know there will be an error because L is too much there. Force over area, we are dividing it. That is stress by strain. So that you can see we are doing it together, we are in it together. You don't need to cram things. You need to follow through. Follow the process. So force by A is stress, then extension. Should we take extension as E now from now? Or I don't want to use that L. Extension I'm taking here, divided by the original length, we take L. I hope students understand this. So from my illustration, we can continue that Young modulus Y is now equals to F by A. We are dividing the answer by E by L. From what I said now, my dear students, now you are going to do something for me very quickly, which I will not partake. Now, you are going to make F sub of formula my way. These are ways I teach in classroom those days. You are going to make Y sub of formula. I said Y force. The force acting on that body sub of formula. You are going to also make E sub of formula. Let's see how far you can do that. So making F sub of formula directly, if you are following through, the force will now be equals to, this is what you can do from cross multiplication. Well, you might not even, you may decide not to disturb yourself. Because if you make a sort of formula or you make a E sort of formula, it's very easy to know that the answer will be equals to this will multiply L and this will multiply E. But if you are not so good in that, you can just cross multiply. So you know it is F over A. I'm not supposed to show this. I'll just show it for some of us that we are beginners. So F by A is equals to, you see, you have Y multiplied by E by L. Yes or yes. This is I say YE over L. I hope you understand that. I've only cross multiply. I'm looking for eraser. Eraser, please come up. Okay, fine. I think eraser is back to life. Now, from there, we have by L. What am I doing? If you cross multiply, you're going to see you are going to have YFL again. So all this you can run away from all these, but for understanding sake, then you have FL is equals to YE A. That is yeah. Don't mind me because that's one thing about me. I make it what the class so funny so that you can always move with it. That is yeah. You understand? Yeah. This is an English word, yeah. So we write it as YAE anyway. But the same if you write YEE or YEE, you are deriving it yourself. So here you can say F is equals to what directly? F equals to what? As you can see, divide both sides by L. You can say L divided by A. So you say Y. You see, this is YEA by L, as you can see. So somebody can say YA over L times what? Times E. Same thing. I hope you understand this now. It's the same thing. What have I done? Because yeah, you can see YA times what? Times E. Then everything divided by what? The same thing anyhow. So this is the first. Now, directly here, I will not waste time this time. I make E soil formula so that we don't waste time. From this point now, you understand? Let's make E soil formula directly. That means we are dividing both sides by YE. So you can say E from this side will be equals to, directly, my dear student, this will be FL will come on top. Then you are dividing both sides by YA. Remember, it is by YA. Then it is be what divided by YA. YA. So which most time we write as the E is the same thing as saying F over YA times what? Times length. Anyhow you are writing it, what matters is for you to know the expression of the force and the expression of what? Of the what? Extension. What is Y? Young modulus. What is A? The area of the cross section of that particular string. As you can see at my back, the string is having a cross section. This is cross section A. So directly we can say. So when we say work is done, and from early classes we can continue. We have this is the last section under this. So we are going to do it together. We are in it together. We can say, yeah, we said work is done. When work is done, what happens, my dear student? Potential energy is being stored. Work is force times what? Distance in the direction of motion. So directly, we just have to put a substitution to what we have talked about. And if we do that, we can calculate the work. So we say when work is done, some kind of what? Potential energy is what is given. Remember from Hooke's law, F is equals to K, because now the wire is behaving exactly like a what? Like a spring, having a force constant K and an extension E. So from here, the force constant K, place which we need to understand, is now what is here. So the force constant K, this is it now, which you said that the constant of what? The constant of the formula. Because when you say, I said, sorry, this is the constant, you can see F is equals to what? KE from what? In spring, which we have discussed. Look at the formula for here, for wire now. What do we have? F is equals to KE. We have by the force constant K. Now you can conclude if you relate. I hope students are following. I am not the kind of teacher that has prepared what I want to say. It is by the flow of what you are doing. So you can see K here is equals to what? What is K here now? Gamma, that is gamma, which is the symbol of young world. You say Y. We have been saying Y. It doesn't change anything. You say YA divided by L. So if anybody asks you to calculate the force constant of what? Of a wire that has been stretched, do you understand? The formula for the force constant of a wire that has been stretched is given directly as this in numericals. It's very important. That means what I'm saying is that a wire is also behaving like what? Like a spring. So because the formula of this one is gamma A or YA by L, open the bracket, you have what you have K, which is more or less like what that means. What this is the way we relate our K. For those who are wondering, you can see the K here is what is inside this bracket. I hope students are following. And I hope you are getting this. So keep that in mind whenever you are asked to calculate the force constant inside the wire or any material that has been stretched, you keep it in mind that this Young modulus multiplied by the area divided by
We said when work is done, what happened, guys? Somewhat energy is being stored. So potential energy that is stored, potential energy in physics, is denoted by U. You can always keep that in mind. So the potential energy stored, because we know now that it is behaving like what? Like a spring or strings. Anyhow you call it. Now, and we have learned that is what half what K E squared from the knowledge of what? From the knowledge of strings, which we have discussed. So now in wire now, this is not, this is wire that we are considering. So we are going to substitute the value of all these in terms of wire. So in terms of wire, my dear student, we are doing it together again. I'm not the only one in it. We are in it together to solve physics and to know physics. It will now be half. What is the first constant, my dear student? What's the first constant? That is a YA, or you say gamma A by L. We are multiplying it by what? E squared. What is E? Look at E, my dear student. E is what? You have, you can write E as FL, anyhow. Say FL over gamma A. You know it is E squared, right? All squared. Any problem? I have substituted the value here. I have substituted it as E and it's R squared. So what I do now is what? I get cancelled out what I need to cancel. So let's cancel it out together because I'm not the only one in it. We are in it together. What happened? Gamma A gets cancelled out, right? Remember, this is square. One gamma A still remain here. Do you understand this? Very good. What happened again? One L gets cancelled out. Remain what? Remain one L. Then I've cancelled this what? Is square. So directly we can say the formula we use from what we have, we are in it together. There's one L, there's still one L. Hope you remember. There's still one L. We have FL, 1 by 2, that is half. Please communicate. FL over what? Over gamma what? Gamma A. So this formula you have to keep in mind, which you can write in your own way, if you want to write it in your own way. But keep this formula in mind. We said half multiplied by FL then times gamma A is the formula we use for this particular thing. So very correct. So FL over gamma A, we have a times FL over gamma A. So this formula, you have to keep it together in mind, because if it is not kept in mind, you might be asked to calculate the amount of elastic potential energy stored, which is what we are doing. Any problem with this, please talk. If you have issues, I can actually re-explain. I think we don't make any because it is exactly the formula which I have kept in mind for a long period of time. So, but this is how to derive that for the sake of the revision. I hope you understand how I cut. And if you don't know how I cut, you can do your own one by one. FL square means F square times L square. Gamma A square means gamma square times what? A square. Then you cut. You can see what I did. Gamma A will go away. The main one gamma A. This is the gamma A. Now FL is double here. Remember FL, this is F square. Oh, this is F square. That should have been a problem. You can see that is it. Please, I would have actually screwed that. This is F square L over gamma A. That's the formula, please. Think that is why sometimes you need to review. So F square, that is the formula. F square L over gamma A. Hope you understand now. F square, the one L here gets cancelled, will remain one L. And that is the formula to calculate the elastic potential energy stored, or you say generally potential energy stored in a wire. I hope you understand that. And in continuation to that, we still have one more, the energy density, which is also very important. And to do that, my dear student, I am going to demarcate this slide. I'm going to demarcate. I need to demarcate because to have space, derivation is not always easy, but we just have to do it for understanding sake. So I will use this slide to start. And if it is not enough, I'm going to use the other part. Now, because I have one slide to explain anything I want to do. And again, about that, we can say energy density. Now, this is the potential energy you write as well. What is the symbol? U, right? Or if you are not so good in remembering U or recalling U, write P. At least you know P, potential energy. So now here, from here, we can say energy density. Now, you can ask in theoretical to define energy density is defined as the ratio of what? Potential energy, that is U, divided by the volume. So keep it at the back of your mind in theoretical form of questions. If you are asked to define energy density, is the ratio of the potential energy of the wire or the whatever divided by the volume. From what we have just studied, my dear student, what is the answer for potential energy? 1 by 2 F square L divided by what? You are dividing it by what? Gamma A. Then what is volume? Volume is always area times length, right? Remember, volume is what? Area times length. So this what distributing that, you can write it in your book to follow through. Because if you are not writing while watching videos, you always going to have difficulties in understanding well. So you have to be writing so that you do it yourself. This is A times L. Let's take it together. We take it in sequence for understanding sake. So let's do that, guys. What do we have at the numerator? Half, or basically you can say FS square, whatever, F square L divided by gamma A. Or you say S squared over gamma A by 2. Or another person can write it like this. Let me show you one way. Because now we want to do something. Before I cut, you know, I'm dividing by A and L. L, we cancel A, all those things. But I want to rephrase this one here. Look at this, guys. I'm not doing any magic. Is what you can look at. F square L times 1. Is it not F square? That's F square L. You follow through. What is 2 times gamma A? That is what? 2 gamma A or 2YE. If you're not so good in saying gamma. Is equals to, okay, divided by rather. Is it not divided? Divided by, what is this one? AL, Abi. What is A times L? AL. Are you guys following? So in continuation, you can now say this is F square L over 2Y or gamma A times this one we call 1 over what? AL. What happened? L gets cancelled out, right? And A will not cancel out. What am I having, guys? I have F square. I'm dividing that by twice of gamma A squared. Any problem with it? Any problem with it so far? I believe this is not an issue. Now, remember, this is F squared, this is A squared. Are we there? Now, to continue that one, I'm going to continue on this side. And if I continue in this slide, I can now say the energy density, continuation from this side, energy density I have to manage is now equals to density is now equals to, you can see L has get cancelled out, we have area. A is the area. Now let's be careful because we need, what is force over area? You know, I have S squared here. You can write this formula as a 1 over 2. I hope you understand because there's an invisible what, arbitrary one or whatever you call it there, multiplied by F squared, which is F times F. Am I communicating? Over 2, why is it 2? The 2 has come outside. Yeah, we have over gamma A times A, right? Times what? Times gamma. Please talk if you have issues with this. Any issue? I have only continued what I have here for understanding's sake to come here. So directly, I want to do some stuff that you guys know. My dear students, what is force over area? Is that not stress? They call that force over area is stress. Force over area, force over area. That is stress. That is half times force over area is stress square. Are you getting it? This is stress times stress, as in force over area is stress, force over area is another stress. Then 1 over gamma. Now, let me show you. Now, 1 over gamma, I can rephrase gamma. Remember, what is gamma? Young modulus. Young modulus. Is that not that? Now, what I have here is 1 by gamma. So what I can turn 1 by gamma, inverse of gamma. Remember, I've explained that in the last class. And if you want to prove inverse of gamma, what is gamma? Gamma is F over A times E over L. Now, what is strain? Extension over original length. So what you're having is like saying the strain is coming up, as in this is what I'm trying to say, guys. Let me show you, because everything can be what? You know, gamma is equals to what? F over A, Abi, divided by E over L. You can see it here, because I have little space left here to explain. Now, if I say 1 over gamma, what happened? This will come up as in 1 over, it means 1 over this thing. Then what is under we? It means 1 divided by, as in 1 divided, I hope you are following, 1 divided by this, because I have, this is times 1 over gamma here. Like, do you understand? So now 1 over this one will be 1 divided, it's just the pity I have little space, 1 divided by the expression of gamma. No, gamma was F over A over what? E over L. What happened when it returns times? This, what is under will come up, what is up will come under. I hope student gets that. That is how I come about my changing. Now, 1 over gamma will now be equals to, from what I have, I hope you are following, it will be what? E over L over what? F over A. What is E over L? Yes, students, strain. What is F over L? Stress. So what I'm trying to say here for you to understand is it will cancel out. Very good. So now I have F over A is stress. F over A is stress. 1 over gamma is now times what? Strain over stress. This is the way we relate. Then directly I can cancel out. What cancel? Stress gets cancelled out. So we say energy density from formula is now equals to what do we have left? Half times stress times strain. This formula you have to keep at the back of your mind anytime because it is applicable in solving a lot of numerical questions in advanced physics and also in ordinary level physics. So keep that in mind that the energy density is given by formula half stress times strain. It's easy to know the formula by heart. So to derive it, it takes what? Extra meticulousness. You have to be careful, and that is what meticulous means. Now, that is that about that. And about the SI unit, it is measured in what? Joules per meter cube. Please, it is very important also to know the SI unit. You know it's even simple. Potential energy per unit volume, excuse me. Volume is a meter cube. Energy is measured in joules. So joules per meter cube is the SI unit of energy density. And this is where we are going to stop. The next thing we are doing now is the quick illustration on what we have discussed according to the what? To the student questions that they always bring out. I have numerical chapters on all the topics. These are concepts. We only pick 1 or 2 questions, which are not, for me, they are not standard enough, but it's just, we can't talk about concept without solving 1 or 2 things. So let's see the question I was picked by the student. I prepared the slide, and let's quickly go through it. Now, about the questions we have. Fine. The first question, according to this, is fine. We have a spring of length 25 centimeter is extended to 30 centimeter by a load of 150 attached to one end. What is the energy stored in it? Energy stored in it. So as we have studied, we know the formula for energy stored in wire. And if you don't know, it is very simple. But this is a spring now. My dear student, this is not a wire. So, and we remember, we can recall, we talk about that. So what? It is a question that the organizer actually brought, we have to solve. For wire, remember, wire behaved like a string, but for wire, it was even from wire, we were able to what? Bring the formula of that of spring. And for spring, that we're able to bring the formula for wire. Remember, the formula for wire is not this. You remember, because for wire, the value of K was derived in what? In the previous slide. If it is wire now, you have to get what? Put the value of K here, then you use your formula. Then for this, energy in spring, this is spring. So this question is on spring, and energy in spring is half K E squared. Ke is the extension, K is what? The force constant. In fact, so far you know that F is equals to Ke in spring. So you can also conclude that what? You can change this formula also in your own way that E equals to half Fe. So anyone that favors you, you can use in the parameter. That is why sometimes you need to do illustration. This is for spring. You know, we discussed about wire, but we use wire at spring. So that is the topic because they are together. And that is why you need to understand the relationship. Now, here directly we can just solve. Here in this question, are we giving anything? We are giving the force. Can you see? So that means this will be favorable. And we are given the extension 30, 25. What's the extension? 30 minus 25. It has been extended by 5. Have it 30 minus 25. Remember, this is in centimeter. A good physics student, you always know that you have to convert it to meter. How do you do that? You divide by 100. That's 0.05 in the meter value. So directly substitute the value in the formula that favors you. You can say energy is equals to 1 by 2 multiplied by the force. What's the force? 150. You are multiplying all answers by 0.05. Which formula did I use? The second one that doesn't have square. If I'm using this K, I will have to get K from what? F equals to K. You understand? Then if I make K sort of formula, because you might look like, how did I come about that? K is what? F by E. If you put K as F by E here, what happens? One E gets cancelled out. You have FE. That is the way we relate all this stuff. So directly we can say 2 can cancel this. 2 goes in 150 75 times. So directly we punch our calculator to get 75 times 5 by 100. You can punch calculator, is allowed anyhow you want to do it. And directly you can cut if you are the type that love cutting. And if you don't like cutting, you can multiply. 75 times 0.05 is going to give you what? Directly with calculator, the answer we are having is we have 375 or 3.75 joules. Not 375, 3.7, because it is 375 divided by 100. That's 3.75, 3.75 joules to be question answer. The next one is the ratio of tensile stress to tensile stress is what? Longitudinal stress. Please note that. Tensile stress to tensile strain is called what? Young modulus. Remember, Young modulus, shear modulus is shear stress over shear strain. Modulus of elasticity is the general constant that comes, which are divided into 3 types. I hope you are following. Bulk modulus, we've talked about bulk modulus. Bulk modulus is given as a volume stress over what? Volume strain. Remember that? And Young modulus, which is the answer to the question, is what? Tensile stress over tensile stress, or you say longitudinal stress over longitudinal. So please be mindful of longitudinal in some question, because they know tensile is common, and learner might decide to give you in terms of that between. So we have last 2, I guess. I don't know. Okay, there's still one more slide here. I think okay, fine. Now this one we have to do that. Now we have a load of 20 Newton on a wire. You can see this wire now, very good. A load of 20 Newton on a wire of cross-sectional area 8 times 10 to the negative 7 meters square produces an extension of this. Calculates the Young modulus of the material. Young modulus formula is known by us. Young modulus formula, Young is Y. Even you can see it at the back of me right away. You can see it's stress by strain. I'm going to say F by A. Remember this? Stress over strain. Extension E over what? The actual length. We've discussed about this. What we need to do is just to distribute 5 values. And we are so lucky in this question that the SI unit are in meter. Let's put the value. The first is what? 20. We are dividing by the area. Where's the area? By the student in meter square. You can see 8 times 10 raised to the power negative 7. Say minus 7 is also correct. The extension produced is extension is 10 raised to the power negative 4. We are dividing it by the actual length. The actual length of the wire is 3 meters. So calculator can finish up, but we have to reduce our own. You know, from what I said, I think FL over AE directly. If I'm the one, I will just say FL over AE, which is the same thing as what we have discussed. But if you are not so sure, you start cutting one by one. Please, it is allowed. Do it in the way you only understand. So, and that is the essence of studying. So you have, if you don't know FL over AE, let us take your own way method so that we don't have issue. This is 20 over 8 times 10 to the power of negative 7. We are dividing. You can see this is division. When it turns to times, what happens? This will come, it will flip and it will change. This is times what? 3 over what? 10 raised to the power negative 4. I hope students understand it. And if you don't understand, we can do it together. 20 times 3 is 60. We are dividing 60 by 8 times 10 raised to the power. In this is minus 7 minus 4 minus 11. So remember what happens? 60 is 6 times 10. Hope you know that 6 over 8 times 10 raised to the power. I've done 60 to 6 times 10. My dear student, it is not important you follow what I'm doing. If your exam, JUPEB, IJMB, WAEC, and NECO, GC, and the rest in our country allows calculator. For some questions, maybe a little bit of post-UTME, some schools, most schools will not allow calculator. So note that. And if they give you this type of question, you might try to solve without calculator. That's why most of the time we have to reduce it. And I'm teaching on how to, it's not compulsory. Punch your calculator. In fact, directly from your natural display, you have the answer to that one. Directly, you can see. So now we say 6 by 8. Why is 6 by 8? 6 times 10. So this is 10 raised to the power 1. What I'm doing is that when minus 11 comes up, it will be plus 11. You know, this is like saying a raised to power m over a raised to power n, elementary class. a raised to power m minus n. See, 10 raised to power 1 minus 10 raised to power minus 11. So minus minus will be plus. So that is 1 minus 1 plus 11. 1 plus 11. What's that? This is 10 raised to power 1, just like this one now. 10 raised to power 1 minus 11. I hope students can see this. So what I did was the 10 raised to is like a here minus, there's a minus here, and it turns this one towards plus. Minus times minus 11 times 10 raised to power 10 raised to power 12. That is it. So it's easy for me to break 6/8 down, and I can say 2 can go here 3, 2 can go here 4. 3/4 is 0.75 times 10 raised to power what? 12. So which I can move by 1. I can make this one 7.5. What have I done, guys? I have moved 1. Like what I've done here is that if I say 7.5 divided by, and you can see this is 75. I can make it 75 or 7.5. I've only moved 110. And if I move down 110, I'll subtract it by from here. And so by 11 should be correct. And Young modulus has SI unit. Please note that Newton per meter squared. Stress has no SI unit. No, I said stress. Strain has no SI unit because length divided by length will what? Meter will cancel meter. Stress has SI unit for these two. The same thing to Young modulus. So you can confirm that I can make mistake. That's why I love taking you through my solution. If there's any mistake, it's what you can correct. It is not a problem. And about the last question for this, we have the energy per unit volume. What is that? Energy density, right? Energy per unit volume of the wire is given by the relation. There is an option. I think the student wants us to derive. Because we have derived, we don't need to waste time. Energy per unit volume is given as what? Half stress times strain. Remember the formula? This is what you are going to say in the option. So always keep it in mind, because if there is a numerical question, the question will only ask us to solve by using the formula. So this is where I am going to stop, and this is the end of our elasticity topic. Don't forget to subscribe to the channel, and again, make sure you share for people to gain and have the good knowledge of physics as you are trying to get. There's no what? There's always love in sharing. So see you soon. Have a wonderful time. Bye.